Hello everybody, welcome to Blue Marble Science. This is part one of the testing and measurement phase for the Cavendish experiment. The Cavendish experiment is used to measure the universal gravitational constant. It's that thing we call Big G, and it appears in the present day version of Newton's gravitational equation along with Einstein's field equations. Now if you're not familiar with this experiment, check the description section of this video and you'll find links to several of my previous videos that describe Cavendish in detail. Cavendish is a sensitive torsion balance, and the balance is housed in this mahogany enclosure. Why mahogany? Well, no particular reason. It would have been a wood that was readily available to Cavendish in 1798. That's what he used, and so that's what I used. Two large lead balls, one you see here, and one that's just barely visible on the far side, are suspended from a beam that can rotate, and that allows me to position the balls opposite either end of the enclosure and very close to the enclosure. Here's one of the large balls. It's 6 inches in diameter and it has a measured mass of 22.03 kilograms. It's made out of lead, and we use lead for a number of reasons. First of all, it's a very dense material. An even more dense material that would have been ideal would have been gold. But I couldn't find anybody willing to provide 44 kilograms of gold, so we went with the much less expensive lead option. But the real important reason that we want to use lead is because it is a diamagnetic material, and it's critical that we use something that's diamagnetic to eliminate any possibility of a magnetic influence. Now the torsion balance is actually a horizontal pendulum that gets its restoring force from the torque induced in the torsion wire when the balance is forced to rotate. It consists of three primary parts: a wooden beam that acts as a spreader, a torsion wire from which the beam and two small masses are suspended, and two small lead balls. When the external suspension beam is rotated, it places the large balls at opposite ends and on opposite sides of the enclosure, and that brings the large balls into close proximity with the enclosure and the small balls. This results in a force of attraction between the large and small masses, and this is the force that we actually measure. But how do we make that measurement? Well, what we really need to know is how far the end of the torsion balance moves. What Cavendish did was attach a vernier scale to the end of the torsion balance and then provide a window through the end of the enclosure where he could look in and take those readings. When you look through the window, that's the view you get. But how do we read that? Well, the vernier scale is at the top. The lower scale is the fixed scale, and those divisions are 1/20th of an inch. Hey, don't blame me. That's what Cavendish did. I just copied it. If we look, we can notice that the 0 on the vernier scale is just left of 0 on the fixed scale. So we would call that negative 0 point something. But what is the point something? How do we read that? And it's really quite easy. All we have to do is just look and see which line on the vernier scale matches a corresponding line on the fixed scale. And in this case, it's the fourth line. So we would read this as negative 0.4 divisions. This is an effective method of making the measurements, but there's actually a much easier way of doing it. We can take a laser and reflect it off a mirror that is mounted on the torsion balance and project that on a target some distance away and amplify the amount of movement of the torsion balance. This is the laser, and it's the same laser that B.M. Furbaugh used in his Cavendish experiment. B.M. was kind enough to let us use it. There you can see the first surface mirror, and I know somebody's going to ask this, so I'll go ahead and tell you. The brass screw you see sitting there is what I use to fine-tune the level of the torsion balance. I just move that until I get the torsion balance perfectly level. So with this arrangement, what ends up happening is we magnify the amount of movement of the torsion balance by a factor of about 10. That means if the end of the torsion balance moves 1 millimeter, the laser spot moves 10 millimeters, or a little more. And that makes it quite easy to read. This should give you a pretty good idea of the apparatus and how it operates. Now let's talk about preliminary tests. After completing construction of the experiment, I went through several months' worth of observations and measurements looking at the stability and repeatability of those measurements. I wanted to look at two different masses for the torsion balance, a 330 gram mass and a 780 gram mass. And I wanted to look at various types of torsion element. This is very time consuming to do, not time consuming so much in the way of actual working time, but time consuming in the sense of calendar time. Anytime I change something, it requires a period of a day or two for the balance to stabilize, for me to be able to recenter it and be able to collect any meaningful data from it. And then you have lag time if you need to order additional material like a different type of wire and so forth. What I ended up concluding is that either of those masses, 330 gram or 780 gram, is perfectly acceptable depending on the torsion wire that you select. And while copper wire and stainless steel wire worked, what worked the best was carbon steel guitar string. It's readily available, easy to find, and it produced the best results in terms of repeatability. But another part of the preliminary test had to do with identifying potential sources of random error. Every experiment has errors, and some of those errors are of a systematic nature, while others are just random in nature. Systematic errors are the simple ones. Those are the ones that we can correct for. For instance, if we're using a scale that always registers 5% too much weight, we can simply reduce every measurement we take by 5%. But there are other errors that are totally random and we can't reproduce it, so we can't correct for it. These are some of the things I considered as possible sources of errors. One was uneven distribution of mass in my shop. I wondered if that could have any effect on the measurements I was taking. So I took some of the more massive objects and moved them to different positions in the shop to see if it had any effect, and in fact, it had no effect at all. Another potential source of error would be temperature variation. Now I know I can hold the temperature out there within about plus or minus 1 degree centigrade. So I intentionally increased the temperature by 2 degrees centigrade and then reduced the temperature by 4 degrees centigrade, in other words plus or minus 2 degrees. And again, I saw no effect on the measurements. Air movement within the shop is another potential concern. There is an air conditioning system out there, and when the fan is on, there is a little bit of air movement in the shop. So I decided to test that to see if it was having any effect. And once again, no effect could be measured. But the movement of masses during the experiment was a different story altogether. There are two masses out there that can have an effect. One is the overhead door. When it's raised, we can see a distinct effect on the position of the torsion balance. And another mass is simply me. If I move around the experiment and get too close to it, I can also have an effect. So while those are potential sources of error, the solution's relatively simple. Leave the door in position, and I just need to stay out of the area. And that's what I did. But another source of error is static electric influence. I saw some very clear indications that we were seeing some static electric influence, even though the lead balls were always electrically tied together and tied to the electric ground system. The wooden case of the enclosure was developing a static surface charge, and that static surface charge on the enclosure would cause the torsion balance to move. So static electric influence is definitely a concern, as would be magnetic influence. Now, I never saw any indication that we were having any magnetic interference, but it's still possible even though we didn't observe it. So some changes were needed to address these issues. In terms of the static electric influence, the solution is fairly simple. I lined the interior surfaces of the lower chamber with copper foil to eliminate that problem. Secondly, rather than depend on the electrical system ground, I decided to install an 8-foot copper ground rod just outside the shop. So now the static shield inside the enclosure, the table that the enclosure is sitting on, and the lead balls, both interior and exterior, are all tied to an 8-foot copper ground rod. And as soon as that was done, the electrostatic influence went away. Now, as I mentioned, I never saw any indication that we were having any issue with magnetic influence. But just to be sure, I decided to replace the steel hanger rods and clevises for the large masses with brass, and that should be enough to eliminate any magnetic concerns. In this picture, you can see that copper foil lining inside the enclosure. And here you see the steel hanger rod on the left. This is before it was replaced. But if you look in the upper right, you see the brass clevis and the brass hanger rod that's now installed. So what were the conclusions? This apparatus is perfectly capable of making repeatable measurements of the level of force anticipated. 330 gram small masses on the torsion balance will produce adequate deflections and were selected for the initial test series. And finally, a 0.007 inch diameter steel torsion wire provides adequate sensitivity when used with those 330 gram torsion balance masses. This, by the way, is not done just by guesswork. Let me show you a spreadsheet that I've been using since before construction began. The highlighted cells are inputs. I initially developed this spreadsheet before I ever started the construction of Cavendish. The reason I developed it was to be able to predict the performance of a specific combination of masses and torsion elements. There's really only two things I'm interested in. One is the period of oscillation, and the other is how much laser deflection I expect. Now, the period of oscillation needs to be short enough that we'll be able to run the test from a practical standpoint, while the amount of laser deflection needs to be large enough that we can make accurate measurements. And the spreadsheet has done a great job in predicting that for us. I may do a video one day on the physics that's involved here. The main point I wanted to make, though, is that this is not being done just by guesswork. We can actually calculate what the oscillation period and laser deflection should be. To summarize the first phase of testing, I did 16 tests in total. I eliminated the high and low test, and that's a pretty normal procedure. And that leaves us with 14 tests that are included in the data set. Now, earlier we talked about random errors and systematic errors. There are a couple of systematic errors with the Cavendish experiment that need to be addressed. The first one is the oscillation period reduction that we need to do due to non-ideal mass distribution of the torsion balance. Well, what does that mean? Deflection of the torsion balance beam is essentially due to the force of attraction between the mass of the large and small lead balls only. The beam itself contributes very little to this. On the other hand, oscillation period depends on the total moment of inertia of the beam, the lead masses, the balance weight, etc. We need to know the force of attraction between the actual lead masses. Therefore, what we do is determine what the oscillation period of the balance would be if the wood beam had no mass. Now, this correction is small. It makes about 1.5% difference. But we need to include it if we want to get the correct value for big G. There's another systematic error that we need to account for, and that is a G correction due to the gravitational influence of the large masses on both the torsion balance masses. Let me show you a picture that'll help you understand. Now, while the large mass is primarily exerting a force on the small mass that's nearest to it, it also exerts a small force on the little ball that is furthest away from it on the other end of the torsion balance. And that results in a force that's actually the wrong direction. It's the same as a slight reduction in the actual force of attraction between the small and large masses. It's only about 0.2%, but we need to take that into account anyway. Now, Cavendish picked out about 4 other systematic errors, none of which really made any difference. So I've chosen just to ignore that. One thing that we absolutely have to do is measure the period of oscillation. And I found that the most accurate way of doing that was with a time-lapse video. Let me show you that time-lapse video, and I'll stop it at the measuring points. I chose the minimum that occurred at 3 hours, 37 minutes, and 33 seconds to start the timing. That's 3:37 a.m. Man, I have got to get a life. Anyway, now we count 8 complete periods, and that minimum occurs at 5:37 and 43 seconds. If you do the math, you'll find out that's a total period of 1 hour, 59 minutes, and 59 seconds. Divide that by 8, and you come up with 889.875. Just round it off to 890 seconds. That's close enough. That's how the oscillation period measurements are made to get the level of accuracy that we're looking for. Now I want to show you a video of how we take the beam deflection measurements. If you've watched any of my live streams, you've seen this 3-camera view before. The top panel is the laser projected against a scale that's graduated in millimeters. The lower left is just a view of the lower part of the enclosure, and the right-hand view is looking in the window that's on this end of the enclosure, so you see the vernier and the fixed scale. To do this demonstration, I had allowed the large masses to stay in this east position for a period of about a day. So the laser is dead solid and reading 193.5 millimeters. Note the time of 8:31. I'm going to start the video at this point, and you'll see me move around on the far side and move the large masses into the west position. At this point, I'm going to speed up the video by a factor of 10. Watch the laser to see the reaction of the torsion balance to movement of the large balls from one position to the other. The torsion balance reaches its maximum indication of about 245 at 8:39, and then it starts back downscale. I'm going to skip ahead an hour or so to a point where the oscillation has been dampened quite a bit. At 10:01, we record another minimum of 216, and as we continue to watch, we will see that the maximum value in this oscillation period is about 229. Taking the average of 216 and 229, the resting point would be 222.5. Now, subtracting 193.5, the original position, from 222.5 gives us a deflection of 29 millimeters. For the actual test, I waited for an oscillation period where the spread between the high point and the low point was 10 millimeters or less. That gave the most accurate center point estimation and the most repeatable results. And speaking of results, all of that leads up to the test results. This is a spreadsheet summarizing the 14 tests that were conducted. You'll see in the red square the calculations required to determine the value of G. All of that was covered in a previous video. You'll find every one of those variables listed in the table above. I don't think this requires a lot of additional explanation. Let me just show you what these results indicate. The accepted value for G is 6.6743 times 10 to the minus 11th Newton meter squared per kilogram squared. Our measured average value is 6.63 times 10 to the minus 11th Newton meter squared per kilogram squared. The data has a standard deviation of 0.31 times 10 to the minus 11th, and the error is about 0.7% lower than the current accepted value. Now, just to give us a way to look at this a little better, I did a scatter chart, and you see that down in the bottom right corner. The numbers along the x-axis are just the test numbers. The values for G are plotted along the y-axis. And note that the y-axis begins at 6 times 10 to the minus 11th and goes up to 7.4. So you're seeing a compressed upper part of the graph. Now, if you're not accustomed to looking at this sort of data, that might look like a real mess, but this is actually pretty normal for this sort of test. I wondered what the Cavendish data looked like. Now, bear in mind that Cavendish was not calculating G, he was calculating the density of the Earth, so his actual numbers are quite different. But analyzing his data the same way, we see this. And you see it doesn't look a lot different than what we have. His standard deviation is a little bit lower, but he's got more tests. So what are the possible next steps? Well, I would like to replace the torsion balance with the 780 gram small masses and use either a .007 torsion wire out of carbon steel or a .008 beryllium copper wire. I've got the beryllium copper on order, but it remains to be seen if that stuff has sufficient yield strength to support the weight of that torsion balance. We'll see when we get the wire. If that works out, I'd like to repeat at least part of the test series. I don't know that time is going to permit me to do another full 14 tests or not. We'll just have to see about that, but I'll at least try to do a few. But you know, one of the things I've heard people say is that the only thing this proves is that lead attracts lead. And it might be fun to try some different materials as a qualitative demonstration of mass attracting mass. Now, I can't imagine why we need to see lead attracting cantaloupe or canned tuna fish being attracted to buttermilk, but that seems to be a point of curiosity. So we'll certainly try to do something along those lines. Warning. This may turn into an egg experiment. Well, with that, folks, thanks for watching. And thanks so much for all the support we've gotten over the past year. Hope you guys liked it, and if you did, don't forget to hit the like and subscribe button down there. As always, a shout out to the Patreons and PayPals, the people who have supported this from the beginning. It's really appreciated. And I know you guys know who you are, but in case you've forgotten, just read the next couple of slides. I'll bet you'll find your name on there. With that, I'll catch you guys on the next one.